Hello and good afternoon, everybody. I am Steve McKechnie. I'm a structural engineer and I have worked at Arup now for something like 35 years. Here are some of my favourite projects from over that time. Today, I've chosen the title Making Zero Carbon a Reality. I've chosen that title because I think it's an important subject. And I think it's a subject that the tall building community needs to grab hold of. I do sometimes hear some of my climate aware colleagues saying that we must turn away from tall buildings because they, by their very nature, are wasteful and resource hungry. But I say that ain't necessarily so. I hear some other colleagues saying that we must reuse structure, that it is wrong to build anything new. Reusing structure is definitely the right thing to do, but people will continue to need homes. They will need to stay warm and safe and to work and to feed their families. If we are to facilitate that sustainable development, then we will need to build new. What we must not do, of course, is to build in a way that damages the earth. There's another group who believe that timber is the only material we can use for engineering without shame. Now, I love timber. I love to look at it and to work with it and to design with it. It will be massively important as we build an environmentally sensitive world over the next 30 years. The trouble is it's combustible. We can fire engineer it and fire protect it, but if we are going to house people in tall buildings, we need to be sure that they are safe from fire. And I am keen that we keep tall buildings available and viable and delightful as an option for creating new homes and offices. Cities are better places when they're dense and busy, when there's footfall and commercial activity, when walking and cycling are the most convenient option because the destinations are close by and the countryside, in turn, is left open and available for the many forms of life and biodiversity to flourish. Tall buildings enable that density to happen. So this afternoon, I'm going to take you on a short journey. It's a tale of three tall buildings, if you like. Two are real, one is a design study. We start at 52 Lime Street. A beautiful building, clean, sharp, incisive. Geometric planes of glass create a crisp but understated silhouette. It enhances the city of London and provides 4,000 people with a place to work, or it will do once we're allowed to go back to work. We designed this building to generate value. Building users value the quality and the shape of the space. They want continuous, uninterrupted floor plates where teams can see each other and collaborate effectively. They want a clear connection to the outside world through story height glazing. We designed a building that delivers this and delivers a 25% improvement in carbon emissions from its MEP systems compared to the building regs benchmark. We also minimized material use in the structure wherever we could. We used vertical pre-stressing in the core because of the unusual building geometry to reduce the wall thickness. We used integral dampers in the frame to minimize lateral accelerations, and we used digital design and fabrication of the beam sections to minimize steel use in the floors. This reduced carbon dioxide emissions from the construction of the steel frame, all of these things together, by something like 2,300 tons. And at the same time, we delivered an additional 6,000 square feet of additional lettable area to the client. So that was good. That was an example of how we can optimize the design outcome by using well understood technologies in an effective way. My next tall building is a little different to that. It's almost the same height, but has a different end use and a rather different aesthetic. The Expiatory Temple of La Sagrada Familia is a project I never dreamed I'd be involved with. But in 2015, the team at Sagrada came to us because they faced what seemed like an insurmountable challenge. The tower dedicated to the Virgin Mary that Gaudi had planned was going to be too heavy. It would overload the columns in the crypt, which were some of the earliest parts of the church to be built back in 1880 something. They were exploring alternative construction techniques and came to see us because we have a track record in the design of steel diabrid towers. We saw their plans and suggested that perhaps those cladding panels they had planned in precast concrete faced with stone might be made by pre-stressing the stone, making the concrete unnecessary. Here's a mock-up panel that the construction department built. Those steel rods are tightened, pre-stressing the bed joints together so that they're always in compression, so that they can carry bending moments and shear even when the panel is lying on its side and a whole bunch of people are standing on it. The team was pleased by this. It was a material they could construct off-site and crane into place quickly, even on a site that was mostly dedicated to having visitors visit the church. It soon became clear as well that the structural potential of these panels went further than just cladding. We devised, working with the Sagrada Familia design team, a composite pre-stressed stone shell structure made from the panels. The stone carries the weight of the tower above and the forces generated by wind loads and seismic events. Where those forces want to put the diagonal mullions into tension, we counteract that by pre-stressing. We also looked carefully at how the panels were made, how they would fit together when they came to site. We wanted them to click straight into place without adjustment or additional work. This video shows you kind of how that works. The resulting structure needs no additional frame. It is light enough to avoid overloading the columns of the crypt, and it means that the tower can be built something like 10 times faster on site than it would have been using the old construction methods. By taking a fresh approach to the construction technology, we had discovered a build method that was better, faster, and cheaper. So, what if we could do that for the construction of our commercial and residential buildings? What if we could find a new way of building that massively reduces or eliminates the emission of carbon dioxide to the atmosphere? Research at Drax Power Station has shown that carbon capture is eminently possible using current technology, but it is very expensive. Our society is not yet ready to pay the amount of money that it would cost to absorb the carbon dioxide from the flues of Drax Power Station, but it could. Of course, there's no reason to pay for carbon capture at Drax because wind power is so cheap anyway. That technology, however, could be applied to the production of cement and steel. Jenny, in her previous talk, spoke about the roadmap to zero carbon for the cement industry. Organisations like Responsible Steel and the Climate Group are also starting to facilitate the steps that the steel industry will take in that direction. We, as a society, have not yet chosen to make the change to zero carbon materials, but we will need to. There will need to be a readjustment when that happens in the balance of cost between materials and fabrication processes. Materials will cost more. We will have to use them in a more efficient way. So, what might that look like? Fabrication and construction methods will have to be more subtle. We will have to use our ingenuity and perhaps digital fabrication and design tools to minimize the amount of concrete and steel we use. This has a double benefit, of course, because if we introduce this way of working now, we can generate significant savings in CO2 emissions even with today's materials, just by using less of them. So I decided to have a look at the lowest carbon tall building structure that I could think of as an example for this talk. So I started with floor plates. If we are to build a tall residential building, we need a non-combustible structure and we need 2 hours of fire separation in the floors. A 120 thick reinforced concrete slab will give me that. That's the thinnest I can get. So I took indirect inspiration, I suppose, from our work at Sagrada Familia and from the builders of the late 19th century. They got the most out of their floor materials by forming vaults. I can use a funicular form finding process to get this shape for my 120 millimeter slab. It turns it into a three-dimensional vault. This one will span 7.5 meters very nicely with a set of 36 millimeter diameter tie rods, but you could flex the span to anything to suit your building grade. So those ties apply a thrust at each corner of the vault, and the support from the column applies an upwards force. We tune those so that their vector sum sets off into the concrete of the vault at the same angle as the concrete. At each point, then, across the face of the vault, the vertical loads from the weight of concrete and other loads turn that compression thrust slightly. The locus, then, of that thrust surface makes a 3D funicular surface. This vault is shaped so that it matches the shape of that funicular surface. The result is a very efficient structure. I imagine that this vault might be precast on formwork that probably has been 3D printed, though it wouldn't have to be. It would be delivered in two halves on the back of the truck. Those halves would be paired up with a set of ties and lifted into place on the building frame. The corners would be bolted into place for robustness and to complete the structural diaphragm. With 3 crane lifts, we have 56 square meters of floor plate constructed. And that 7.5 meter span is good because it works well as the depth for a residential unit from core to perimeter. I put 9 vaults together and found that I could fit 6 apartments into that shape. They comply with the Mayor of London standards, and we get in a staircase and some lifts and some risers. If we take 27 of those floors, they fit quite nicely into this arrangement of columns and bracing. I chose that particular arrangement because it is quite an efficient structural geometry. All the columns stay in compression. The story height I chose was 3.25 meters. Apartments have vaulted ceilings that go up to 3.07 meters high with a minimum at the column position of 2.39. I've drawn the ties at their springing points, you'll see, because that's the most efficient place for them. I rather like them there. But you could move them up into above the vault if you wanted to. Right, so the columns and bracing add up to 25 kilograms per meter squared of steel for a tall building. Those ties that we just talked about add another 4. Overall, we get a 27-story building that needs 4,000 tons of precast units and 400 tons of steel to construct it. It houses 156 residential units, that is 10,700 square meters of net sales area. If I add a spread foundation to that, and the one I chose also uses funicular form, I can deliver a building which, using today's carbon factors, has a calculated embodied carbon rating of 99 kilograms of CO2 per meter squared of floor area. That gives it an A+ rating on the iStruct's scores rating chart, beating pretty much every building frame currently under construction that's more than 2 stories high. As we move towards as we move towards zero carbon materials, that rating will of course come down even more, and we will achieve a truly zero carbon generation of tall buildings that are efficient in their use of the Earth's resources and that leave precious space available for other species to flourish. But even now, we have within our grasp a way of building tall building structures with a very low carbon footprint. We can be at the forefront of the move towards zero carbon that's happening right across our society right now. Thank you.